Okay, let's learn some definitions of functions. When a relationship between two variables x and y is such that given any x, there corresponds at most one y, we say we have a function and we write it as y equals to fx. The set of numbers x for which fx is defined is called the domain of the functions. So really in this very long explanation, there are two things we need to take note of. There are two terms, domain and rule, that's very important, and it describes portions of a function. So a function must include both domain and the rule. So what is the domain? This set of values for x, where this capital R letter actually stands for all real numbers, this is what is defined as the domain. And this portion of the function, the expressions that we usually work with, x cubed plus 1, we call this the rule. So altogether, the entire statement here, we call this a function. Okay, alternatively, we may write it this way. So the only difference here is we use the mapping symbol, and the other side we put fx as x as the bracket with an equal sign. So it's just two different ways of writing, but it means the same thing. It defines the same function. Okay, this is a textbook definition of a function. You see this in many textbooks. Let's read it together. Given two sets of x and y, a function fx mapped to y is a rule or relation. We've mentioned some of the terms here. You see the word rule, which associates with every element. So we call this, I would call this an input into the function. So we call them by the variable x, and a unique element y, which very often I would call them the output of function, as you can see in the diagram below. So for a function, we often work with some certain values. For example, we can have fx equals to the expression we see earlier, x cubed minus 1. So if we input x equals to 1, for example, we end up with an output of value equals to 0. So in this case, if I input 1 into a function defined by the rule x cubed minus 1, the output obviously here would be the value equals to 0. So we call this input the domain. And what comes out, the set of values, the entire set of values that comes out from the function, we call this a range. So all of these are some terminologies that you may want to read, but very often what is very common here at CAEM is for you to make sure you know what's the domain and what's the range of a function. When we define a function, there are two things we mentioned. Every element of x has a unique value of y. So let's look at some examples and let's explore and see if these are actually functions. So let's look at A. A has one A, B, C, D. Element C actually has not been mapped into any output. So because of that, it doesn't fulfill having every element being accepted. That means not all input that you put in generates an output. So in this case, we call this a relation. This is actually not a function. So not a function for A. Let's look at B, part B now. Look at this diagram, and we have three inputs A, B, C. All of them generates an output. So B gives an output of value 1, C gives an output of value 2. It doesn't really matter that 3 is not accepted. It's just a distractor here. So B actually is a function. Okay, so let's look at example C now. C has all its all its input value 1, 2, 3, they all generate an output. But unfortunately, there is some confusion here because the value of 2 as an input actually gives us 2 outputs. So what happens is the function is not able to be defined with a unique value of y. Unique means only one output. So if somebody says you're very unique, there's only one of you, isn't it? So then in this case, because 2 of these inputs have variance in its output, so the computer, for example, cannot quite decide what is the output. So part C is not a function. So when we say some relationship is not a function, we call this obviously a relation. Okay, so D, let's explore D. Similarly, you see when the value of 5 is entered into this function, it gives rise to 2 outputs. So note, D is not a function, not a function. And let's look at E. E, every element has one unique output. C has one unique output. It doesn't matter if the output is of the same value. Okay, it's fine. So in this case, E is defined as a function. Lastly, example F. This is a very nice and tidy function. Every one input gives rise to one unique output. Coincidentally, f is a function and it has a name for it. We call this a one-to-one function. We can define using graphical method if an expression is a function by using the vertical line test for functions. And the vertical line test simply means that if I draw any vertical line across, let's call it x equals to a can be any real number, and as long as it cuts the graph at 2 different points, for example, at any point on the graph, you realize that it does not give rise to a unique value of output. So for example, x gives rise to either y1 or y2, so that is not the definition of a function. So in this case, the blue graph is actually a relation. But if we look at the orange quadratic graph, any vertical line just cuts, gives a x value and one unique y value. So as long as it cuts at exactly one point, we call f a function. So that's the vertical line test, and we use it to help us explain if graphically if a set of x and y values is called a function. 3 examples here to determine if the following are graphs of a function. So we've learned the concepts of vertical line test. So as long any vertical line, let's call it x equals to a, where a is any real number, and it cuts the graphs at only one point, we call this a function. So y equals to x to the power of 5 is a function. Look at B. If we draw any vertical line and it happens to cut the graph at more than one point, so we call this a relation. This is not a function. So in this case, the graph of y squared equals to x cubed is a relation, not a function. Looking at C, any general vertical line cuts the graph at only one point, so yes, this also is a function.